Your oxygen saturation is just effectively how much oxygen there is in your blood. So in order to understand how pulse oximetry works, we first need to understand how oxygen is carried around the body. When we breathe in air, the oxygen diffuses across specialized membranes in our lungs and into our bloodstream. But the oxygen doesn't then just float around in our blood. It binds to specialized molecules called hemoglobin, which carries it around the body. When hemoglobin has oxygen bound to it, it's called oxyhemoglobin. And when there is no oxygen bound, it's called deoxyhemoglobin. Pulse oximetry is based on the principle that oxyhemoglobin and deoxyhemoglobin absorb red and near-infrared light to different extents. Oxyhemoglobin absorbs greater amounts of infrared light and lower amounts of red light than hemoglobin. This scientific principle can be seen in practice, with arterial well-oxygenated blood appearing bright red due to the fact that it scatters more red light than deoxyhemoglobin. And similarly, deoxygenated venous blood appears much darker because it absorbs more red light. It's a fortunate scientific coincidence that hemoglobin has these properties, because red and near-infrared light penetrates the skin and soft tissue much better than other forms of electromagnetic radiation of around the same wavelength. Pulse oximeters exploit this difference in absorption profiles to detect the level of oxygenation within the blood. Pulse oximeters emit two wavelengths of light, red light at 660 nanometers and near-infrared at 940 nanometers from a pair of small, light-emitting diodes located in one arm of the finger probe. The light that is transmitted through the finger is then detected by a photodiode on the opposite arm of the probe. From this, the probe can calculate the relative amount of red and infrared light absorbed, and this can be used to ultimately determine the proportion of hemoglobin bound to oxygen. But this does present a problem. When we measure oxygen saturation of blood, we want the measure of oxygen saturation of arterial blood, not venous. This is because the arterial blood is still oxygenated, having not delivered the oxygen to the tissues yet, whereas the venous blood has already delivered oxygen to the tissues and is mostly deoxygenated. Because of this, only arterial blood can supply us with a reliable reading of how well we are oxygenating our blood. The ability of pulse oximetry to detect oxygen saturation of only arterial blood is based on the principle that the amount of red and infrared light absorbed fluctuates with the cardiac cycle. This is because the arterial blood volume increases when the heart contracts, because the heart is pumping oxygenated blood to the peripheries, and similarly decreases when the heart relaxes. Whereas the blood volume of veins and capillaries remain fairly constant throughout the cardiac cycle.